Using the setup and our definitions from the previous video, we're now ready to state our Mason's rule formula. And so remember, this formula is going to give us the single transfer function for a system that's represented by a signal flow graph. So our single transfer function, g of s, of course, by definition is going to be equal to our output, c of s, divided by our input, r of s. And so our Mason's rule formula is relatively simple. All we have in the numerator is a summation from n equals 1 to k of t sub n times delta sub n divided by delta. All right, so that's it. So now we need to define what some of these terms are in our summation on the right side over here. But other than that, it's pretty straightforward. So I will note that this notation is slightly different than what you'll see in the textbook. I've adapted it because I think that this makes a little more sense how I have it here. So let's define some of these items then. So our k, which is sort of the upper limit for our summation, is the number of forward paths in our system. So number of forward paths. So for instance, in our previous system, in the previous video, we saw that we had 2 forward paths, so our k would have been 2. Our t sub n, which again, that n is varying from 1 to k, is the nth forward path gain. So the nth forward path gain. So in the previous video, the system that we looked at there, we would have had a T1 for our first forward path and a T2 for our second forward path. So finally, we have 2 more items. First, let's define our delta, which is in the denominator. So our delta is going to be defined as 1 minus the sum of our loop gains. So we had defined those as L1, L2, L3, and L4 in the previous video, but we might have more or fewer loops than that in a system. We are then going to add the sum of our non-touching loop gains taken 2 at a time. So non-touching loop gains taken 2 at a time. Sorry, I have to go on to this next line here. So in the previous video, we had sort of 3 combinations that would have fallen into this category for non-touching loop gains taken 2 at a time. And then after that, we're going to subtract the summation of the non-touching loop gains taken 3 at a time. So non-touching loop gains taken 3 at a time. And then beyond that, we would add in the summation of our non-touching loop gains taken 4 at a time. So maybe not put a 4, let's spell it out. So 4 at a time. And then we would subtract the sum taken 5 at a time, so on and so forth. So in our system from the previous video, we did not have the ability to take our non-touching loop gains 3 at a time because we only had sort of 2 loops that weren't touching each other. We didn't have 3 loops, all of which were not touching any of the other 2. For more complicated systems, of course, this delta gets harder to evaluate. So the last item that we want to define is delta n. So our delta n is just going to be the delta. So delta, let's see if I can draw a proper delta, with the loop gains that touch the nth forward path removed. So with the loop gains that touch the nth forward path removed. And so one note about this delta sub n here, so the equation in the textbook is incorrect. However, the explanation immediately following that equation is correct. And so you'll notice in the lecture notes or in the items posted on Canvas, there's something called the Mason's rule correction. And so that's just a more detailed explanation of why what I've written here in the notes is correct and where the error is in the textbook. But just watching this video and knowing the definitions of all of these items, you'll be perfectly fine.